Okay, so we're going to work on the rational root theorem. Sometimes it's called the rational zero theorem. When I was in school, we learned rational root theorem, so that's what I still call it. Depends on what textbook you have. So, we've done some factoring, we've done synthetic division, we've done long division, we've done all these things. We're trying to get to the end goal of getting like a fifth degree polynomial and just being able to start from scratch, finding all the roots of this fifth degree polynomial. That's our goal. That's what we're trying to get to, okay? Today, we're going to learn about a lot of things that will help us find that root, but we're not going to actually find the root yet. We're just going to go towards that goal, okay? And the first one that we're going to look at is the rational root theorem. Now, the rational root theorem in regular English, okay, says that all of your roots will be factors of the last number in a ratio to the first number, okay? We call it p's over q's. So let's say that you've got this qx to the fifth, blah, 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 plus p, okay? There's a big, long polynomial in here, okay? Huge polynomial. It's a fifth degree polynomial, and it has all these numbers, okay? If a rational root exists, now do you know what I mean when I say rational? What's a rational number? We're going way back to like Algebra 1. 1 is a rational number. Yeah. What else is a rational number? 5. Yeah. Is 3/5 a rational number? Yeah. Anything that can be a fraction. See? Rational. Whoops, stop right there. If it can be a ratio, it's a rational number. Like 5 over 1. That's 5, and it's a fraction, so it's a rational number. Okay, so the rational root theorem says that any of the possible roots that are rational, that are real, not imaginary, not those crazy ones that we find with quadratic formula, not those, but like the normal, pretty, happy numbers that we love. Oh yes, thank heavens, it's like pretty. If those exist, they're going to be a ratio of the factors of p to the factors of q. The factors of p to the factors of q, okay? This is where your possible rational roots come from. Really good. All of this is starting to like, this is the lesson where everything starts coming together and making sense. Alright, so what's a factor? Like, what are the factors of 8? Yes, okay. Factors are what go into that number. So the factors of 8, like 1 and 8, because 1 times 8, 2 and 4, because 2 times 4. So those are factors. So what we're going to do is we're going to list all the factors of p, we're going to list all the factors of q, and then we'll make ratios out of those numbers. And that will be the list of numbers that we can draw from for our roots. Okay? So let's look at an example here. Let's say that we have p of x equals 3x to the 4th That's the problem we're looking at, okay? And we're going to work on p's and q's. Alright, what's in our P place?
14.
14. What's in our Q place? 3. Alright, what are all the factors of 14? 1. Okay, but let me ask you something. If I multiply 1 and 14, I get 14. What happens if I multiply negative 1 and negative 14? You get 14. This is actually negative 14, so what happens if I multiply a negative 1 and a positive 14? Or a positive 1 and a negative 14? You got to put plus or minus on all of these. Yes. Alright, what about my Q's? Plus or minus 1, plus or minus 3. So, these are not the possible rational roots. The possible rational roots are P over Q. I just make a list, okay? That's what I just make a list. All of these over the first one, which that's going to be easy because it's over 1. So is that really even considered a fraction? No, not by normal people. So 1, 2, 7, and 14. And then all of those over 3. 1/3, 2/3, 7/3.
Did we do this last year?
Yes. 14/3. And you know what's wonderful? In Algebra 2 now with the new Common Core stuff, because a lot of you in here didn't have Common Core Algebra 2. We do this in Algebra 2 now. We're doing it right now in Algebra 2. It's chapter 4. Awesome. Those are all of our possible rational roots. There's 16 of them. 16 possible rational roots. You're like, 16? Holy cow, I gotta test 16 numbers? Well, you did have like all numbers in all of infinity, and we've knocked it down from infinity to 16, so that's pretty good, right? Yeah, and I'm going to show you a couple of other ways to knock it down even more. But I want you to be really, really good at finding your P's and Q's before we start eliminating even more of them. Is my coffee in the way? Can you see? Because I'll just drink it. You need anything?
I'll drink it for you.
Alright, let's turn it. What's in the P place? 4. So what do I have for all my factors of 4? Nope. 1, 2, and 4. Great. What's in my Q place? 6. What do I have going on there? Yes. Alright. So if I'm looking at P over Q, it's going to be 1, 2, and 4. Then 1/2. I already have 1. I already have 2. See, I already have that. Well, I don't want to get out of order. Here. There's no need in writing the 2 again because it's already there. There's no need in writing the 1 again. It's already there. So let's go with 2/3. It's going to be 1/2. 1/3, right? Four thirds. 1/3. No, I'm sorry. 1/2. 1/6. 4, 2, 4/3. 2. That's it. 1, 2, 3, 4, 5, 6, 7. 16 of them again. So you try one. I'll give you some nice numbers so there's not too much to have to. Find all your possible rational roots. It's 5. And then we have Q, which is 2. So how about P over Q? Very good. Very good. All right, let's talk about one way to knock out some of these, okay? Let's talk about upper and lower bounds. Upper and lower bounds. These are exactly what they sound like, okay? They are the biggest number and the smallest number that you're going to use. All right, so upper bounds and lower bounds. Let me explain to you what happens here. Upper bounds, we start with a number, an integer, 1, okay? And we put 1 through the problem using synthetic division. And if our goal is to come up with no negative numbers in the bottom, in the answer. And I'll show you what we're talking about in just a second, okay? If there are any negative numbers, it is not an upper bound, so then we try 2, okay? So you put 2 into the problem. And what you want is you want to have no negative numbers. All positives on the bottom. If we have all positives on the bottom, then that's great. 2 is our upper bound. If we don't have all positives, then we try 3. So we try to find the largest number that gets us all positive. Now, if the lead coefficient is negative, then we want to have all negatives. Basically, we don't want to have any sign changes on the bottom. We want the bottom to have no sign changes. That's for our upper bound. For upper bound, we want no sign changes. Lower bound's just the opposite. For lower bounds, we want every sign to change. We start with -1 and we put -1 in, and we want it to be positive, negative, positive, negative, positive, negative, positive, or negative, positive, negative, positive. Like we want every other sign to change. And we put numbers in and we test these numbers until every other sign changes. So you might be thinking, how is that going to help me? That just seems to be adding work to it. Well, it actually does help. Let's just think about this first list that we had. And let's say we're testing numbers, and we get that the upper bound is 2. 2 is our highest number. Well, guess what? If 2 is our highest number, we know we don't have to test 7. We don't have to test 14. We don't have to test 7/3. We don't have to test 14/3. So we just knocked out 4 of them. And then maybe we do another test and we find out that our lower bound is -1. Oh, that would be fantastic. Because then you wouldn't have to test -2, -7, -14, -7/3, and -14/3. So you really knocked out a lot of the numbers that you have to choose to look for and to test. So upper and lower bounds can help you. Now let me show you how it's done, because I can tell you that it doesn't really mean anything. Okay? So let's say p of x equals 2x to the fourth plus 7x squared minus 4x minus 4. So on this one, p over q would be 1, 2, 7, 14, 1/2, 7/2, 14/2. Those would be all of the possible rational roots that we'd have to test. So we're going to do an upper bound and a lower bound test. Upper bound, start with 1. Oh, I skipped one. It's 4, 2. I didn't skip one, I wrote it down. It should be 2x to the third. Alright, so I bring down the 2. 2. What?
Did you not have to test 14 over 8?
Yeah, I don't have to. I would have missed it. So that's a 9. 9. 5. 5. Oh, -9. See, it's not all positive. So 1 is not an upper bound. Let's try 2. 2, 4, 11, 22, 18, 36. Alright. 2 is the upper bound. See, all these numbers, I don't have to worry about any of them that are bigger than 2. 7 is out. 14 is out. 7 over 2 is out. No need to even test them, because 2 is the biggest number. Okay? 2 is your boundary. So we just went from all of these numbers, and now I've knocked out about 3 of them. Okay? That's what testing your upper bounds does. It doesn't tell you the answer. It does not tell you an answer. Unless you accidentally find a 0, which I've done that before, and it's like God has gifted me with some saved time and paper. But it doesn't tell you the answer. It just helps you eliminate some of the others so you know how to get to the answer. Okay? So now, lower bound, same process. We use negatives. And we don't want them to all be the same sign. What do we want? Every other sign. Okay, so that's going to be 2, -2. Oh, okay, see right there? Is that every other sign? I'm not going any further. I don't need to go any further. It's not every other sign. This is supposed to save time, okay? Let's try -2. Negative, no. 2, that's a -4. Nope. Not doing it. Still -3. 2, -6. Nope. But we're getting closer. We're getting closer to that sign. 2, -8. 1. And that's going to be a +4. That counts. That counts. -4. So nothing is going to be smaller than it. So we just knocked out -7 and -14 right there. Okay? So upper and lower bounds don't give you the answer. They do not give you the answer, but they do help you eliminate some things when you're trying to find the answer. The last thing I want to talk to you about on eliminating answers is Descartes' rule of signs. Alright, Descartes' rule of signs says that when you have a problem, just like you haven't done anything to it, how many ever sign variations that there are, how many times the problem changes signs, that's how many positive roots you have by multiples of 2. Okay, let me show you what I mean. See, this is a positive, and it goes to a negative. That's one sign change right there. A negative that goes to a positive, that's another sign change right there. No sign change. Sign change right here. So this particular problem has 3 sign changes. So it has 3 positive roots, or, go by 2, 1 positive root. How does that help me? Well, you know this problem has at least 1 positive root. So you can test positive numbers. You know one of them has to work. It has 1 positive root. One of them has to work. And if you stumble upon 2 of them, it doesn't have just 2. It has 1 or it has 3. So if you find 2, you know there's a third one there somewhere. So you can find that third one. That's for positives, okay? Positives, you just check the signs exactly like they are in the problem. Negatives, you have to actually put a negative through and then count sign changes. So for negatives, you're looking at negative x to the 4th minus 5 times negative x to the 3rd plus 5 times negative x squared negative x minus 6. Okay, now we remember, we've done this before, negative and even end up being positive. So that's just going to be x to the 4th. Negatives and odds change signs. It's still going to be plus 5x minus 5x minus 6. Now, listen closely to what I'm going to say. It is not sign changes from here to here. It's sign changes through the problem. Okay? It doesn't, it is not how many times did the sign change from the original to the new. That's a positive, that's a positive, that's a positive. Oops. There's a sign change right there. See that? No sign change. So this problem has, for sure, 1 negative root. It has 1 negative 0 or negative root. Because it has 1 sign change for the whole thing. Okay? That's Descartes' rule of signs. You look at the original tells you the positives. And when you put a negative through, the negative tells the negative. And in all of this, do we know what a single 0 is yet? No, we just started eliminating it. Which is good if it tells you like there's no negatives. You just eliminated half of your choices, so that's good. Or if it says, hey, there's no positives, half of your choices are gone. That's excellent. Tell me these sign changes, alright? You can tell me this one. Let's see. 2x to the 5th plus 3x to the 3rd plus 5x squared plus 8x to the 7th. Tell me, look at this, how many positive roots does it have? How do you know? There's no sign change. So there's no positive roots. No positive roots, none. The sign never changes. Okay? Now, put a negative through there. And tell me how many possible negative roots there are. Alright, let's see. If I put a negative through, that's going to be negative 2x to the 5th. That's going to be minus 3x to the 3rd. That one doesn't change. That changes. And that does not change. So, sign changes. Negative to a negative, no change. Negative to a positive, there's a change. Positive to a negative, there's a change. Negative to a positive, there's a change. How many negative roots does this have? 3 or 1. You know it has at least 1, and then if you find a second one, you know it has at least 1 more. It does not have 2 negative roots. If you find 2 negative roots, there's another one out there. You know it has at least 1. Okay? Again, we are not finding zeros today. We are just finding ways to get to those zeros. Okay? It's gonna all come together. Look at this page I just put on your paper, on your desks there.